So this class will keep talking about continuous random variables. Okay, so what is the idea of continuous random variables? Now we have x that is going from omega to r, and the image of x is not countable. Okay, so we're going to put in quotation marks. The idea for a continuous random variable that you should always remember is that the probability that your random variable x is equal to some x in R is equal to 0 for every x in R. Okay, so this is almost the definition. This is almost the definition of continuous random variable. Okay, just to remind you, so a little bit more informally, the definition: x is a continuous random variable if the probability of x less or equal than a given number a is equal to the integral from minus infinity to a of density f of x, let's call it little x dx for every a in R. Okay, so where f of x is called the density function of x. Okay, and the property of the density function is f of x is positive everywhere, and the integral from minus infinity to infinity of f of x little x dx has to be equal to 1, because this is the probability that capital X is in R. Okay, so one of the things I think I might not have made such an emphasis is that this density function of x allows you to calculate anything about this capital X. Okay, so what we had seen is that, for instance, if you want to calculate the probability that v so v is less or equal than x less or equal than a, what we obtain is that this is the integral from minus infinity to infinity. This is the integral from v to a of f of x little x dx. Okay, and this can be written as the difference of the two integrals, as we had seen in the other class. But this is more general. Okay, so for any well, I should be a little careful with this, but for any subset A of R, okay, there is some measurability problems, but for almost any A subset of R, the probability that X is contained in A is equal to the integral over the set A of f of x dx. Okay, and so the almost any here one has to be a little careful, but the idea is that here, what we have shown by this property here, this is when A is equal to the interval BA. Sorry for, yeah, usually it's the interval AB, but in this case it's just BA. So the point is that now we could take similarly A equals to VI AI, and we take the union from I equals to 1 up to a capital N, and then where all of these intervals are separate, and now we can say the probability that X is in the union of all of these intervals okay, and so on. So all of these little pieces are A. So the probability that X is in A is going to be the integral over all of these intervals of your density function. One can take a limiting thing of this process, and then one can consider A that is in the sigma algebra generated by intervals. Okay, this is what is usually called the Borel sigma algebra. Okay, but one has to be a little careful with these things in terms of measurability. But anyways, so the idea is that this density function gives you all the information of X given in any set, not just in intervals like this. Okay, so you can actually calculate what this thing is in every interval, in every subset of R, or at least almost every subset of R. Okay, so why did I want it to stress that part is because what we were looking last class was the case where X, when we have more than one random variable. So the definition is X and Y are jointly continuous if there exists a function, a density function f of x, y going from R2 to 0 infinity, such that f of x, y of a v is equal to the integral from minus infinity to a of the integral from minus infinity to v of the density f of x, y, little x, little y, dx, dy. Okay, and this is, this is the density function of both things, which is the probability that x is less than a and y is less than b. Okay, and f of x is if there exists a joint density function. So f of x, y here is considered, it's called the joint density function of x and y. Okay, so what is the next thing? So here we are considering intervals of the form. So x less or equal than a and y less or equal than b. This is of the form a, which is equal to minus infinity, comma a union times minus infinity, comma b, which is a subset of R2. So if we draw it, let's say here is x, here is y, this is A, this is B, and so morally this set is given by this. Now, something that we did last class, and maybe I didn't stress that much. So let's say that we want to compute the probability that, let's say, the notation might be a little hard. C is less or equal than X, less or equal than A, and D is less or equal than Y, less or equal than B. Okay, so the probability of this guy is going to be actually equal. This is a difference that we did last time. Is the integral from C to A of the integral from D to B of f of xy of little x, little y, dx, dy. Okay, so the way of doing this is by decomposing it in a bunch of integrals of this form. Okay, and this is what we did last class. But in general, okay, so if you look at the A associated to this, okay, so this was A here. So A in this case would be C, comma A cross D, comma B, which is a subset of R2, which if we do graphically, this is A, C, V, D, and we would have this little square here. Okay, and this is A. So now, in general, we could have a set A that looks the following way. Okay, so this is A. So what you can do for this type of sets A, so okay, what is going to be my claim? My claim is that A is in the sigma algebra of sets which are obtained as union of these guys. Okay, so what you're going to do for A is going to start considering it into little squares. So we approximate A by a little square here, here, let's say here, then you put another one here, another one here, another one here, here. Okay, so the idea is that we can approximate for every relatively smooth set A, we can approximate it by unions of disjoint squares, rectangles. So we can approximate it by, and here, infinite unions. They are infinite unions, but countable. Infinite unions, countable, of disjoint rectangles. Okay, so it would be, we consider AI, which is the union from I equals to 1 up to, this would be AN, which is the union from I equals to 1 up to N of well, following this notation, CIAI times DI comma BI, such that, so this is a disjoint of disjoint rectangles where all of these rectangles are disjoint, such that AN converges to A when n goes to infinity. Okay, I'm not going to say what type of this convergence is, but then what we are going to show, I mean, we can do this in a way that is done from below. Okay, so we can use continuity of probability. We can use continuity of probability to show that the probability that x comma y is in AN converges to the probability that x comma y is in A, and this here was the double integral in AN, where the double integral in AN is basically the sum from I equals to 1 up to n of the integral from Ci to AI, of the integral from Di to Bi of the density function, and this converges to what we are going to be calling the integral over the set A of the density function f of xy. Okay, so what I was doing all of this, so I chose, here I had chosen a set A which had no particular shape or something, so in particular we could consider A, so we could consider A the points in R2, x comma y in R2, such that x squared plus y squared is less or equal than 1. Okay? So a set like that is not a perfect square, it's not a perfect rectangle, but it can be approximated. This A can be approximated by rectangles. Okay? So then if we wanna find the probability that x squared plus y squared is less or equal than 1, okay, this thing here can be restated as x comma y, which are the random variables, is in the set A, which is this set A here, is going to be the double integral over A of f of x y x y dx dy. Okay, so before I was talking about like general, like super general sets, but even something as simple as this, we can, so particularly in something simple like a circle, which is simple in the sense that is some really smooth object, but at the same time is not exactly equal to one of these products. Okay, but even though it's not exactly equal to one of these products, by taking a limiting procedure, we can actually get that the probability that the random variables are here is equal to the integral over this disk of this thing here. So here I would put the integral over A of, here I would say x squared plus y squared is less than 1. Okay, and this integral here, you can probably write it as the integral from minus 1 to 1 of the integral from 0 to square root, the integral from 1 minus the square root of 1 minus x squared, and 1 minus 1 of minus x squared of f of x y x comma y dx dy. Okay, so if we have access to the joint density function, we have to consider these integrals, which we might be able or not to calculate, to get the probability that these random variables, the sum of the square of these random variables is less or equal than 1. Okay. Okay, just to remember something, because we might use it later on in class. So, theorem, if x and y are jointly continuous, and g going from R2 to R is continuous, then the expected value of the random variable g of xy, okay, so this is a random variable, the expected value of e of g of xy is going to be the double integral, so this is over R2 of g of little x little y of f of x y little x little y dx dy. Okay, and the proof is the same as before, and it can be seen similar to what I was saying in terms of approximation. So depending of what you're taking your function g continuous can be approximated by all of these things. So the integral of here, so the integral of being in a particular set A is going to be the same as integrating against this joint density function in that particular set A. Okay, so you can see these things in a similar way. Okay, so the proof of this, the expectation of g of x y is going to be equal. So it's going to be equal to the density, the integral over c of the density function of f of g x y at z dz. Okay, sorry, at little z d little z. Okay, and the way that you calculate this density function is what we're going to see now, but it's similar to the way that we were doing it in the case of the. So okay, now we could do a change of variables. So the probability that g of x y is equal to c is going to be the integral over the inverse of in a particular set. So let's forget about this proof, which is a little harder for now, and let's look at something slightly simpler. Is what happens when g of x comma y is equal to x plus y. Okay, so when we sum random variables. So here we are going to consider, okay, so let's consider z, which is a random variable, which is g of x comma y, which is x plus y. So in this case, we want to find what is the probability that z is less than a parameter c. This is going to be equal to the probability that x plus y is in z. So another way of writing this is the probability that the pair x comma y is in a set A z, where a z is equal to the joint pairs x, y such that x plus y is less than z. Okay? So if we do this thing in R2, let's say that this thing here is z, this thing here is z. Okay, this is little x, this is little y. So x plus y less than z is this set here. Okay, this is AZ. So the probability that x comma y is in AC is the integral over AZ of the joint density f of xy of little x, little y, dx, dy. So, but this set AZ can be written in this particular way. So the way I could write AZ is by integrating for a particular x. I can integrate y. So for every x, I can integrate y from this point down. Okay, and so on. So what does this mean with respect to the integral? I could integrate from minus infinity to infinity of the integral. So now, so x is going from minus infinity to infinity, but y is going from minus infinity to z minus x, okay, to this line here. So this is going from minus infinity to z minus x of f of x comma y, little x, little y, and here I'm actually integrating first dy and then dx. Okay, and here we can do a change of variables. Okay, so we change variables and we consider, let's say, u is equal to y minus x. We consider u, which is equal to y minus x, and then we can rewrite this integral as the integral from minus infinity to infinity of the integral from minus infinity to z of f of x, y, x, comma, u plus x, dy, du, dx, okay? And this here is what is equal to y, which we have replaced from the previous one. Now we change the order of integration, and this is the integral from minus infinity to z of the integral from minus infinity to infinity, and I'll put a bracket here, of f of xy, x, comma, u plus x, dx, du. Okay? But what we started was the probability that z is less than little z. So this is equal to the probability that capital Z is less than z, which is equal to the integral from minus infinity to little z of f of z u du. Okay? So then if we look at these two things being the same, it means that the thing between the bracket is equal to the density function of fz. So fz of u is equal to f of the integral from minus infinity to infinity of the joint distribution f of xy, x comma u plus x dx. Now, okay, so this seems like a slightly hard formula. We could actually put this formula back into this and get the proof for this particular g. But now, let's say, what happens if x comma y are independent? So if x and y are independent, then f of xy in little x little y is f of x at x times f of y at y. Okay, so this is an if and only if they are independent. Okay, this is if and only if x comma y are independent. Therefore, f of z at u is equal to the integral from minus infinity to infinity of f of x at x times f of y at u plus x dx. Okay, and this is has to remind you, if you looked at the class for the sum of discrete random variables, this is exactly equal to the convolution. Okay, so this is the convolution of fx with fy at u. Okay, so if you don't know what the convolution is, this should be your definition. The definition of the convolution, so the notation is with a star. The convolution with the density of fx with the density of fy is given by the integral in the whole of r of f of x in x times f of y of u plus x. You get this right? Yeah, I think I got this right. So anyways, this is, we can use the convolution, the definition of the convolution like this. Sorry, I am trying to see what, maybe there should be a minus somewhere. X y is less than c minus x. So I think here I want to put y plus x so that this becomes a z. And so then here you get that we get this is u minus x, this is u minus x, this is u minus x, and all of them here is u minus x. And so then you get the convolution. Okay, so the convolution is with a minus sign. Okay, so let's do an example of this. So let's take x, which is normally distributed, has distributed like a standard Gaussian, and y is also normally distributed as a standard Gaussian, and x comma y are independent. So in this case, what we have is that f of x at x is e to the minus x squared over 2 over the square root of 2 pi. And the joint distribution f of xy, this is by independence, f of xy at xy is going to be the product of these two guys, which is e to the minus x squared over 2 times e to the minus y squared over 2 over 2 pi. And if we look at this, this can be just written as e to the minus norm of x comma y squared over 2 over 2 pi. Okay, where x and y is considered as an R2 vector. Now, what is the density? What is the density of x plus y? So what we had said is that f of z at u is going to be the integral from minus infinity to infinity of, so f of z at u is the integral from minus infinity to infinity of the density of f of x at x and f of y at u minus x. So this thing here is e to the minus x squared over 2 over square root of 2 pi times e to the minus u minus x squared over 2 over square root of 2 pi dx. Okay, so now what we're going to do is expand the square, expand and recomplete the square. Okay, so here the multiplication of exponentials is going to be the sum of their arguments. So what we're going to have is minus x squared over 2 minus, and now minus, let's say, u minus x squared over 2, which is equal to minus x squared minus plus u times x minus u squared over 2. Okay, and so what we should note is that the variable that we're integrating against is dx. So this term u squared over 2 is independent of this integration. So we can actually put it outside. But we want to actually complete the square here. So this is equal to minus x. So if we need to complete the square, this is equal to minus x minus u over 2 squared. But now if I have added, if I have completed the square here, to complete the square here, I have to subtract minus u squared over 4 and add u squared over 4. So here you would, if you complete the square, you get minus x minus u squared, minus u over 2 squared. And then canceling the u squared over 4 with the minus u squared over 2, you get minus u squared over 4. So what we get here is that fz of u is going to be equal. So this part is independent of the integration. So you get e to the minus u squared over 4 over 2 pi times the integral from minus infinity to infinity of e to the minus x minus u over 2 squared dx. Now, so why did we want to complete the square? We wanted to complete the square because we notice this integral is independent of u. Okay? So by taking a change of variables x minus u over 2 equal to x, then, so what we notice is this integral is independent of u. Okay, and so what we need what we end up getting is that this integral is independent of u, and the integral from minus infinity to infinity of e to the minus x squared is actually equal to sorry, so if I had here minus x squared over 2, the integral of minus x squared over of minus x squared is going to be equal to the square root of pi. If I got this correctly. So it might be that, so maybe you want to check this guy, if this is correct or not. But the point would be that then what we get here is so you probably get that this is the square root of pi over 2. Okay, this is the same technique to calculate the integral from minus infinity to infinity of e to the minus x squared over 2. So you can actually do a change of variables and check that this has to be equal to this. Okay. Anyway, so if you do a change of variables, you should end up, this is equal to the square root of 2 pi. And the point is that now we are dividing by these 2. So you will actually going to get the square root of pi over 2. So then what we get is that fz of u is going to be equal to e to the minus u squared over 4, the square root of 8 pi. Okay, and this is the density of z, and this is distributed as a normal with 0 mean and variance equals to 2. Okay, so in general, so just as a reminder, in general, normal with parameters mu and sigma squared is it has density. This has density e to the minus x minus mu squared over 2 sigma over the square root of 2 pi sigma squared. Okay, so in this case, mu is equal to 0 and sigma is equal to 2. Sigma squared those 2 sigma squared. So we might need to check a little bit of the computations, but the idea of following this is that what we started with is that X is a Gaussian it's a Gaussian distributed with parameters 0 sigma here. Okay, so mu equals to 0 and sigma is equal to 1. Y is a Gaussian, which is mu is equal to 0 and sigma is equal to 1. And then if we take the sum of them, we are going to get another random variable, which is also a Gaussian with parameters sigma mu is equal to 0 and sigma is equal to sigma 1 plus sigma 2. Did I get this right? That's a good question. Yeah, okay, so let me check this. Let's say that this is equal to square root of pi. Then if this is equal to square root of pi, what we're going to get here is square root of 4 times pi, 2 sigma squared. Anyways, there is a problem with the constants here, but it's not a big deal. And so then, in particular, in general, if X is distributed as a normal distribution mu I sigma I, and Y is distributed as a, so mu 1 sigma 1, and Y is distributed with parameters mu 2 sigma 2. Somehow I feel like there's a sigma there. Anyways, doesn't really matter. What we're going to get is that Z, so X plus Y, which is equal to Z, is going to be distributed as a normal of mu 1 plus mu 2, sigma 1 plus sigma 2. This is if X and Y are independent. Yeah, maybe I'll go back to this at some point. I'm a little pissed off about the constants, but it's something you can check yourself to make sure that you understood what I was trying to do. Okay, so this is if X and Y are independent. So the example that we saw last class is what happens when they're not independent. What happens when they are not independent? So the example from last class was we consider f of xy, which is equal, the density, the joint density, is equal to 1 over 2 pi square root of 1 minus p squared, the exponential of e to the minus x squared minus y squared plus 2px times y over 2 times 1 of minus p squared squared. Okay, what we show is that if we consider the first marginal, marginal, then x, which is, so the first marginal, which is f of x is at x is equal to the integral from minus infinity to infinity of f of xy dy. Okay, so if we integrate out the y variable, we get the first marginal. Then what we can check is that x is distributed as a normal with parameters 0 and 1. And similarly, y is distributed, the second marginal of this distribution is done in such a way that y is distributed with parameters 0 and 1. And what we can see is that x comma y are independent if and only if f of xy is equal to f of x times f of y. But in this case, this is if and only if p is equal to 0, okay? So the idea is that this parameter p measures the correlation between x and y. Okay, so measures the correlation between x and y. Okay, so this we'll use to introduce the covariance. The covariance between x and y is given by the covariance of xy is equal to the expectation of x times y minus the expectation of x times the expectation of y. So in a sense, you're checking, this can be rewritten, okay, so the covariance of x is also equal to the covariance of xy is also equal to the expectation of x minus the expectation of x times y minus the expectation of y. Okay, so the covariance is measuring what is the relationship between x and y. So when x is above its average, is y above its average or not? So if x is above its average, implies that y is above its average, then this implies that x and y are positively correlated. So whenever x is large, y is large. Okay? So this being positive implies that x increasing implies y increasing. Okay, and this is the notion of correlations. Okay, so in particular, in the case that we were before, so we can look the expectation of x. So for x and y as before, we have that expectation of x is equal to expectation of y, which is equal to 0. Okay, this is because x and y are distributed as normal distributions. So what do we need to know? So the covariance between x and y is going to be the expectation of x times y. And this goes back to what I said a while ago, but I didn't prove. So if we have jointly continuous functions, if we have x and y that are jointly continuous, and we take a continuous function that is going from R2 to R, the expectation of this random variable, which is the composition of G with x and y, is the double integral in R2 of the joint density of G of xy. So the expectation of xy is going to be equal to the double integral of x times y of the joint density f of xy little x dy dx dy. Okay, so let's try to compute this thing. So this is going to be the double integral from x times y of e to the minus x squared plus y squared minus 2p times xy over 2 to 1 minus p squared dy dx. Okay, I'm going to be a little sloppy probably, but the idea is to try to complete the square. So how do we do this? So here, so how do we do this? Okay, so we need to complete the square here. So we are going to get y minus p x. So we need minus x squared plus y squared minus 2p x times y over 2 times 1 minus p squared. This is going to be equal, and this is a computation you just need to make, is equal to minus x squared over 2. And now this is coming out, the fact that you get over 2 is coming out that you are completing the square, which is minus y minus px squared over 2 times 1 minus p squared. Okay, so if you expand this square and then you sum this piece here, you can check that these things are equal. Okay, so in particular, what we are going to get is, if we do this integral here by taking this substitution, we would get the integral of x times e to the minus x squared over 2 times the integral of e, so of y times e to the minus y minus px squared over 2 times 1 minus p squared dy dx. Okay, but now what you could see is that this is the expectation of a random variable. Okay, so this thing here Okay, this is this distribution here up to the normalizing constant is the distribution of a normal variable that is centered at P of x with sigma squared equals to 1 minus P squared. Okay, so the expectation, this guy here is the expectation of this, but what we're missing here is the normalizing constant. So the normalizing constant should be, so this is the expectation of this times the square root of 2 pi times 1 minus P squared. So what we get here is that this thing here is going to be the expectation of this, but the expectation of this is just P times x, because this is the average, mu. So what we get is that this is the integral from x times e to the minus x squared over 2 times P times x times the square root of 2 pi 1 minus P squared. Okay, so I've been a little sloppy because here there was always a normalizing constant, and the normalizing constant was the square 2 pi times the square root of 1 minus P squared. And so if we have it here, 1 over 2 pi square root of 1 minus P squared. So then what we are going to have is that this is going to cancel with this, and we are going to get that 1 over 2 pi square root of 1 minus P squared. So this is just going to be equal to P divided by the square root of 2 pi of the integral of x squared e to the minus x squared over 2 dx. Okay, and the idea, so here we saw that this was the expectation of a random variable, a normal random variable, a Gaussian random variable with expectation p times x and variance 1 minus p squared. So in this case, this thing here is the variance of x. Okay, so the variance of x is the integral of x squared e to the minus x squared over 2 dx, and all of this is just equal to 1. Okay, so the variance of, so in general, so this is a reminder, or actually just something you need to know. So let's say that x is a normal with center at 0 with parameter sigma squared, then the variance of x, which is equal to the integral of x squared f of x, is going to be equal to sigma squared. So this is the variance of x, which is distributed. So the variance of x is equal to sigma squared, and the expectation of x, so let's put it like this. X is a normal with parameters mu and sigma, then the expectation of x is equal to mu, and the variance of x, which is equal to this minus mu squared, is going to just be equal to sigma squared. Okay, so in this case, because x is distributed as a normal with parameters 0 and 1, this is equal to just 1, and this is equal to p. Okay, so then the covariance between x and y is equal to p. Okay, so what we can note that for every p in minus 1, 1, we can define Gaussians. We can define two Gaussian random variables such that the covariance between x and y is equal to p. So for p equals to 1, so one has to be a little careful because the density that we wrote here, this is only valid for p in minus 1 and 1. So p equals to 1 is an extreme case, which in this case, p equals to 1 implies taking x equals to y, and p equals to minus 1 implies taking x equals to minus y. Okay, so if you can see here, this density when p is equal tending to 1 will imply that x is all of the mass is given in the line x is equal to y, and in the case where p is equal to minus 1, all of the mass will be given in the line x is equal to minus y. Okay, so what we defined for discrete random variables before was the correlation coefficient, which is rho of xy, is going to be equal to the covariance of xy over the square root of the variance of x times the variance of y. Okay, so in the example before, variance of x is equal to variance of y, which is equal to 1. Okay, and so then this implies that rho of xy is equal to p. Okay, so there is an observation or remark. Observation is that rho is minus 1 is less or equal than rho of xy, which is less or equal than 1. Okay, and so how does this follow? This follows by the Cauchy-Schwarz theorem. So what is rho of xy? So rho of xy, as we're saying, is the covariance of x, covariance of y. So what we're going to show is that this is, we're going to show this by showing that the covariance squared is less or equal than the variance of x and variance of y. So assume, without loss of generality, that the expectation of x is equal to the expectation of y, which is equal to 0, then the covariance of x, y is equal to the expectation of x, y, and the variance of x is equal to the expectation of x squared, and the variance of y is equal to the expectation of y squared. Okay, so rho, the norm of rho is less or equal than 1 if and only if. So here we have the covariance divided by the variance, the square root of the variance squared. So this is less or equal than 1. The absolute value is less or equal than 1. and we can put it as squared if and only if the covariance, so the expectation of x times y is less or equal than the expectation of x times y squared is less or equal than the expectation of x squared times the expectation of y squared, okay? And this thing here is the Cauchy-Schwarz inequality. Okay, so let's write it as a theorem. The expectation of x times y squared is less or equal the expectation of x squared times the expectation of y squared. Okay, and this is what is called Cauchy-Schwarz inequality. Okay, and the theorem also says with equality, if and only if there exists an A in R such that the probability that AX is equal to Y is equal to 1. Okay, so we have equality in this case if and only if one is is linearly dependent on the other. Okay, so whenever you have a result for X, then you multiply by a constant A and you get Y. Okay, so let's do a proof of this. So what is the proof of this? Let's consider we consider the random variable Z equals to AX plus Y. Let's call it, just so that it's not as confusing, let's call this T, okay? Where T is in R. Okay, so then the expected value of Z squared is positive, and this could be a set of T for every T in R. But in particular, what is this? This is the expectation of Tx plus Y squared, which is positive. Okay, but by using linearity, and expanding the square, this is T squared times the expectation of X squared plus 2T times the expectation of X times Y plus the expectation of Y squared. And this is bigger or equal than 0 for every T. So there's a couple of different ways of thinking of this. Now, we could take T to be the optimal one, okay? So we could minimize over T. So we could find the optimal over T and figure out that if this is positive, this implies this inequality. That's one way of doing it. So in this case, it would be, so what is the optimal? So this is a parabola. This is a parabola in T. Okay, so what we do So if we have a parabola in T, so this is T, and this thing here is what we would call P of T. Okay, and this is P of T. So what we could find is what is this minimum point here. So P of T is equal, so let's call this A, this V, and this C. So P of T is A times T squared plus 2BT plus C. And this is bigger or equal to 0 for every T. Now, the minimum of this thing, so P prime of T is 2AT plus 2B plus 2B. And so at this point here, this is what is T star is equal to 0. P prime of T star has to be equal to 0. So then what we get is that T is equal to V over A. Okay, so then what we get is that P of T star is equal to B squared over A, and there's a minus here, B squared over A, minus 2B squared over A plus C is bigger or equal than 0. So this implies, this is at the minimum point here, so this implies that C times A is bigger or equal than B squared. But now we just need to replace what C, A, and V squared are. So this implies that e to the x squared times e to the y squared is bigger or equal than e, so b squared, which b squared is e to the x times y squared. Okay, and this is the proof of the Cauchy-Schwarz inequality. And to have equality, we need that this point here passes through 0. To have equality, we need that e of c of t squared is equal to 0. We need that e of z t star squared is equal to 0. But this is equal to the expectation of t star times x plus y squared is equal to 0. But now if we have a positive random variable whose expectation is 0, this implies that the probability that t star x plus y is equal to 0 is equal to 1. Okay, so this implies that y is equal to minus t star times x. And you can actually compute what t star is. T star here is e of x times y over e expectation of x squared. Okay, so you can actually compute what minus t star is, and it's given by this formula here. So you can actually compute what is the optimal one in these things. Okay, so this is telling us that our the Cauchy-Schwarz inequality, which implies that the correlation coefficient is between rho of x, y is between 1 and minus 1, and the correlation coefficient is equal to 1 or minus 1, so it's equal to 1 or minus 1 if and only if x is equal to ay. So it's equal to ay with a positive or a negative, respectively. So what am I trying to say here is the correlation coefficient is telling you if x increases, then y increases, if rho is positive. But if rho is negative, it's telling you that x decreases, implies that y increases. Okay, so but when you get to the limiting case where the coefficient is equal to 1, this implies that there is a direct relationship, linear relationship, that x is a times y with a positive coefficient a. And it's equal to minus 1 if there is a negative coefficient. Okay, we're going to stop here today, and then I'll keep going for another class later this week.